Yeah. What I was talking about too.
Yeah.
And that's
Yeah, if anything, a little lecture on consent is probably a good way to start any lecture ever.
true.
Okay, these groups. All groups. Works for all groups. But it's only really good for non-abelian ones. Because all the abelian ones become. Right. Composition series. Something like this. So you have a group, a normal subgroup of it, a normal subgroup of it, a normal subgroup of it, and so on until you hit the trivial group. And all these are normal in the next one, and it's called a composition series. And if it's called a composition series, well, no, if they're normal, that means that you can do the quotient or the factor groups. So this factor group is Z2, this factor group is Z2, the next one is Z2. So, right. So AN is simple, so you have this kind of composition series. For S4, did we do it for S4? No, we didn't do it anymore. For many groups, you can have different composition series. Okay, they're completely different because they have completely different subgroups appearing in them. But what we saw was that when you do the factor groups, you get exactly the same ones. Not in the same order, but exactly the same factor groups. Okay, and what we started doing was proving this Jordan-Hölder theorem, which says that no matter what two composition series you take, the factor groups, which are called composition factors, are always going to be the same for a fixed group. How does the proof go? The proof goes by induction on the order of the group. First case is easy, and it is when the second group in both series is the same subgroup of G. So when the second group in the series is the same, then we can use induction on that second group. And we know that the composition factors that are these factors here and these factors there are exactly the same by induction. And this is the same group, and this is the same group. So this factor group and that factor group must be the same as well. That was case one. Case two is when they're not the same, and then we can go home. No, we cannot. Share is terrible. So what do I want? When they're not the same, I can take their intersection. So this is a normal subgroup. Of G by exercise 10.5. And if I take their product, and that's not the direct product, that's right. take one element from one and another from the other, and take all such products, is also normal. Was that proved somewhere in isomorphism theorems or something like that? Maybe. If not, it's easy to prove directly. So now, so what do we have? We have G, which has a normal, that's actually, yeah, G has a normal subgroup Hn minus 1 times Kn minus 1, which has a normal subgroup Hn minus 1. And the second thing is because so why is this normal in that? If I take any element Hk times any other element from H times Hk inverse, which way, yeah, that's the way I did it. So I want this to be an element of H. That will then prove this is Hk, H dashed, and these two come in K minus 1, H minus 1 along that. So this is in H because in Hn minus 1. Because, yeah, because Hn minus 1 is normal in G. Okay, that's how it is. So now we have this correspondence theorem. It talks about subgroups of factor groups. So if you divide all these by Hn minus 1, you get normal subgroups as well. That's the correspondence theorem. Okay, this is a simple group. Because of the definition of composition series. All the factor groups in the composition series are simple. Trying to find it somewhere in the book. It's tough.
It's obviously difficult in the book, just trying to see where I've got some.
So this is simple, and this is a normal subgroup. How is that possible? Like a simple group is defined by not having any normal subgroups. Well, no normal subgroups other than the identity and itself. So that means that this vector group is either that or that. But that also, by the correspondence theorem, means that this group is either G or Hn minus 1. Okay. And so on. So if this was the case, then you would have Kn minus 1 would be a normal subgroup of Hn minus 1, which is a normal subgroup of G. And so again, between Kn minus 1 and G, you'd have another normal subgroup. But this factor, G over Kn minus 1, is supposed to be simple. So by the same argument that we have here with the correspondence theorem, Kn minus 1 would have to be Hn minus 1, or Hn minus 1 would have to be G, but none of them is possible because case 2 said in the beginning that Hn minus 1 is not Kn minus 1, and Hn minus 1 is the first, well, the second group in a composition series, and that's supposed to be less than G, so like proper subgroup of G. So none of them is possible. It's not possible. Because Hn minus 1 is not Kn minus 1, and Hn minus 1 is not G, and G is simple. So it must be this. Now when we have this composition series, where is it again? Come on. We're interested in what this factor is and what that factor is. So G factor Hn minus 1. G factor Hn minus 1 now is, because G we know is that product, and this is isomorphic to what? Hn minus 1 divided by n, where n was this intersection of the two groups. It says somewhere at the top, and is that intersection. And this is because there is a second isomorphism to the theorem. Well, there's nothing special about H, so you can do the same tricks with K, and you get the first composition factor in the other series is isomorphic to Kn minus 1 factor n. What am I doing? No. This looks suspicious because it is suspicious. It's supposed to be the other way around. This one is the K. It's obvious because Hn, I'm dividing by Hn. You can't say it immediately, but there is a theorem that says it. That's why this notation kind of makes sense. So this Hn minus 1, I'm dividing by K, so I'm left. This is Hn minus 1. Now I'm going to delete that as a cons. So that. So now the induction is you get a composition series which
Used.
used. So you get a composition series for this, for n, n1, n0 is just the identity. By induction, no matter what composition series you take for n, because n is smaller than g, you get always the same composition factors, which has a unique possible list of composition factors now Hn minus 1 contains n as a normal subgroup. And if you continue nt minus 1 you get a composition series for Hn minus 1 by using the 1 for n. And if you do Kn minus 1, is 1 for Kn minus 1. Well, these are simple. This factor here is simple. It's isomorphic to this, and that was simple because we started with a composition series. Same for this one. So it is indeed a composition series now. So this is done. No? So when you look at these two composition series that we're studying, okay, the composition factors for 1. So the list, what does it contain? Well, it contains Hn factor Hn minus 1. Right? And it contains Hn minus, then it contains, by induction, all the composition factors for Hn minus 1, because Hn minus 1 is smaller, there's a unique list for it. What does that list contain? Well, we can take it from this series, right? Because it's a composition series for Hn minus 1, and by induction, it doesn't matter which series we take it from. So it has Hn minus 1 factor n, and all the composition factors for n. So if we take all the composition factors for n, from no matter which composition series by induction, and Hn minus 1 factor n, and Hn, we get a composition series. We get all the composition factors. And for the other one, well, we get Km n minus 1, all the composition factors for Km minus 1. But then we can take this composition series to get them. So this is Km n minus 1 factor n, and all the composition factors for n. Are they the same? Well, this is the same. Kn minus 1 factor n. What did we say it was? Kn minus 1 factor n is isomorphic to g factor hn minus 1, so that's here as well. And kn factor kn minus 1, well, what was it? Yeah, that's this. So that's isomorphic to minus 1 factor. So they're the same. Still about 9.5 weeks to go, and everybody's tired. Like it's
In my defence, I've been tired for about 6 years. So. You sort of really appreciate it.
So now these groups are called solvable, that have only abelian composition factors. Why you? Okay. Why you going? Why are you beating cheese? Okay. Examples. Example 1312. We had that already, yeah? T4. What did it have as composition factors? Well, vector, and vector. All abelian. So it's solvable. Example 1319. I think it's wrong in the book. Wrong in the book. What does it say?
It says,
Yeah. Yeah, okay. It's not completely wrong because they're a bit different. They're a bit odd. But so if you want the composition series for a symmetric group, Okay, so it has A4 as a normal subgroup of index 2, so this factor is Z2, or isomorphic to Z2 because it's index 2, so 2 elements in the factor. This contains as a normal subgroup what? 1, 2, 3, 4. 1, 3, 2, 4, 1. Okay, so this is 12, this is 4. So A4, well, this is isomorphic to the prime peer group. And this, well, the index is 3, I think, so it has to be Z3, because there's no other group in the elements, right? Now they go straight to E, I think. Which is not a composition series, so I want to continue because if you do 1 and 1, 2, 3, 4, and then so this is isomorphic to Z2, and the V4, this factor group is also isomorphic to Z2, and then obviously Z2, Z1, 2. So if you just did V4, well, V4 is not simple. V4, if you skip this one, you get a subnormal series, a normal series, but you don't get a composition series because V4 is not simple. So what they do in the book is they skip this one. So their last factor is V4, but that's not simple. So their series is not a composition series, it's just a subnormal series. But that's okay because their definition is that solvable means it has a subnormal series where all the factors are really. And that's equivalent to it. To finite groups. That's another example. So then, that's part of the example. Another part is that Sn contains An, contains E is a composition series for Sn when n is greater than or equal to 5 because A5 and A6 and so on, they're all simple, but non-abelian. So the composition factors that's 5, yeah. Okay, that's kind of where the chapter ends. Well, exercise 20 is to prove the theorem that G is solvable if and only if Gn is E for some n. What's Gn? Been time for 26 years, you're already used to it. Gn, you don't know what it is because nobody ever told you. So G naught is just G, and G I plus 1 is G I dash. And for any group H, dash is the subgroup of H generated by all the commutators in H. And commutator X and Y is X, Y, which is X inverse, Y inverse, X, Y. That's quite fun. Proof is exercise 20, so that's left as an exercise. You look unhappy. Okay. One. So you take a group. It's so you look at any two elements in it, X and Y. For any two elements, you create X curve. X inverse, Y inverse, X, Y. You put them into a set and you take the subgroup that they generate. That's H dash. G dash. And then you do the same thing with the next one, with the one you got. And then you do the same thing with the one you got. And then you do the same thing with the one you got. In general, they will be getting smaller. Well, sometimes they will be getting smaller and smaller because you have fewer and fewer elements, so you're creating fewer and fewer commutators. And if so, it happens that after a finite number of steps, you only end up with the identity and nothing else. Then the group is solvable. And if it doesn't, then it wouldn't. Read exercise. Why is this? What is this useful for? Useful for. So what? When is a polynomial? That's what Galois said. Solvable by radicals. So when can you solve a polynomial? By just doing roots of things. And it continues, and it comes to a theorem. Regular n-gon constructed using a ruler and a compass. If and only if n is 2 to the k times p1 times p to the root 2 times pn, where the pi's are distinct lemma and all this is covered in Gillian's year 5 unit, further advanced algebra. But by then you will have graduated. So this is why one wants to look at solvable groups, because you can't get there because there's no. So that's probably the end of chapter 13. I'm not coming again because everybody's asleep.
I'm sure we'll be more awake. I'm sure we'll be more awake.